Additive manufacturing represents technologies that build 3D objects by adding layer upon layer of material. In the Delmia powder bed application, we start with a part, geometry of which has been optimized, using applications in CATIA. We then design the support structure, and create a program for the optimized part. We can use additive manufacturing solutions to print any material such as ceramics, plastics, metals, composites, and many more. We can produce increasing complex and custom designs using 3D printing. Today, 3D printing is opening the door to new design possibilities. 3DEXPERIENCE Additive Manufacturing Solutions provides us with the digital tools that will transform industry by shifting it from an expensive design, build, and test approach to developing functional part right first time. Using these solutions, we can optimize the design for weight reduction without compromising the structural integrity of the part. We will see how to use the powder bed fabrication app to 3D print the support structure for an engine of a jet. For generating output for the 3D printer, we will program and analyze the 3D part using these 8 steps. First, we will define the part. Here, it is the joiner part. We will start with opening the data in the powder bed fabrication app. Use the south quadrant to navigate to simulation apps, and open the powder bed fabrication app. We will define the part that we want to produce. Here, we are selecting the part from an already open tab. We can also import the part, then search, and select it. Next, we will define the device that is used for creating a physical part. For example, 3D printer. We will define the machine that we will use to produce the part. We will create a new generic machine. After creating the machine, we will create an accessory on which we will position the product. We will create a build tray as an accessory. We will define the size of the build tray by specifying the dimensions. After creating a build tray, we have to position the parts on the build tray. We will use the build layout command for positioning. First, we will compute the optimized orientation for the part on the build tray. To do this, we will select the part, and then specify the parameters for computation. Click Find Orientation, and then click OK to save the computed orientation. Now, we will create a build layout rule for positioning the part on the tray. By using build rules, we can save process parameters in a rule, to reuse them later in another additive process. We will enter the required parameters for creating the layout rule in the panel, and click OK. When we are producing several parts on a single tray, we will use the Generate Nesting command to position all the parts on the build tray automatically. Click OK in the Build Layout panel. Next, we will create support structures for the part. These support structures help to sustain the overhanging features of parts. Support structures also allow improved heat dissipation to the substrate. We will use the Manual Support Creation option for creating the supports. Select the part from Work Area, and toggle the switch to Support Definition in the Manual Support Creation panel. First, we will choose the Wired Support, and then select with Anchor Supports checkbox. Wired support defines a wire pattern, which is then extruded, to build a collection of vertical panels supporting the part. Anchor support definition provides us parameters for the elements at the interface between the support and the part. We will toggle again to zone definition, and define the areas where support needs to be added. We can also visualize the support zones. Once computed and displayed, we can choose which zones to keep, and which zones to delete. Select the zones as shown, and observe that, upon the click, support is created. Similarly, we will create wired support for the central overhang of the part. Now, we will create tree support for the remaining overhangs. Tree support is created in the form of a tree that comprises a root, a branch, and leaves. Similar to wired support, we will define the support creation parameters and anchor support. Select the zones one by one, to create tree support for each element. Click OK in the Manual Support Creation panel to save the created supports. Now, we will generate and analyze the scan path. Scan path analysis allows us to optimize the manufacturing process by detecting surface defects. We will create a rule to define the rules for the parameters of the scan path. Specify the slicing step, and click OK. Next, we will generate a slicing path, using rules created earlier. Select the part from the work area, and then choose the slicing rule from the drop-down list. We will now edit the scan path definition sequence field, to define the hatching strategy parameters for the scan path. Specify the parameters and click OK. Slicing and scanning path allows us to identify the key zones on a part, and apply scan path definitions on them. We will use the sliders to review the slicing results. After the scanning is done, click OK. Next, we will analyze the scan path. Scan path analysis allows us to optimize the additive manufacturing process by detecting surface defects. We will specify the geometrical and physical parameters for analysis. Geometrical parameters allow us to analyze and compensate for geometrical errors. Physical parameters allow running a physical simulation of the building process that helps in evaluating the shape and size of the melt pool during the manufacturing of the part. We will compute the analysis by keeping the default physical parameters. After the computation, the result of a scan path analysis is displayed as points on the part in the work area. Here, green to blue points show the lack of matter. Yellow to red points show the excess matter. After the analysis is done, we will close the scan path analysis panel. Finally, we will export the generated output into a file. This file will be used to produce the part using a 3D printer. We will first select the part, and then choose the output format. STL format is widely used for rapid prototyping, 3D orienting, and computer-aided manufacturing. We will select the output parameters, a directory where we want to store the file, and then click Generate Output to create the file. Close the Generate Output panel. We will feed this generated output file to the 3D printer to manufacture the support structure of the jet. We started with the objective of 3D printing the engine support structure. We created and analyzed the supports required for 3D printing the optimized part using powder bed fabrication app. After analysis, we exported the generated program output in a file, which will be used to 3D print the engine support structure.